As part of assignments and projects in E92 Principles of Operating System, we have implemented an operating system on a free-scale K70 hardware with ARM processor. The operating system has following features: shell, memory management, file system, and device-independent I/O, system calls in supervisor mode, timers and interrupts, process scheduling, and multitasking. I'll go over each feature in subsequent slides. The OS has a cell which interprets and runs user commands. These are some example commands supported by the cell. These commands draw similarity from Unix in terms of what they do. For example, date prints current date and time on standard output. PS prints list of active processes. Memory management module provides interfaces to allocate and release memory. It implements first fit algorithm to do so. It provides memory protection by allocating stack for each process. It provides ownership of memory to processes. For example, a process can release memory only if it has allocated it. It cleans up memory acquired by a process when it terminates, so it sort of does this garbage collection. Device-independent I/O is implemented using virtual file system. The virtual file system is an abstraction between users and devices. The concrete file systems or devices, such as in-memory file systems, LCD or switches, need to implement a set of virtual file system interfaces in order to hook themselves to virtual file system, and virtual file system has an interface for users which they can use to perform I/O operations in a device independent manner. For example, when user opens a device, a file descriptor is returned, which is a number that can represent a file or a pipe or any other device that user can use to read and write on that device. Operating system provides system calls to users in order to perform certain system features. For example, I/O operations, memory allocation and deallocation. Using system calls, operating system makes sure that users have controlled access over resources, because only operating system should perform certain operations. For example, operating system should decide how to create and allocate resources to a process, or how to switch between processes for multitasking. When user makes a system call, then process runs in supervisor mode with higher priority, so that in user mode certain features are not allowed and only allowed in supervisor mode. Some example system calls supported by this operating system are set get date time to set system date and time, malloc free to allocate and deallocate memory, open close to open or close files or devices, read write to read and write files or devices, spawn kill to create or terminate processes, pipe to perform inter-process communication. Clocks or timers send periodic signal or interrupt, and operating system acts accordingly. For example, increment system time or does process switching. Following clocks, timers are being used in this operating system. Sysdig timer is being used in process scheduling. Flex timer is being used for updating system date and time. I/O operations from or to UART serial communication is interrupt driven rather than polling. The operating system creates an illusion of multiple processes running at the same time. Each active process runs for a period of time or quantum, after which CPU is allocated to next process ready to run. The round-robin algorithm has been used for process scheduling. Each process has its own stack and set of open file descriptors so that they don't interfere with each other's memory or device buffers. Operating system makes sure that resources acquired by a process is freed when process terminates so that they are available to other processes. The operating system maintains this PCB data structure for each process. Every process has a process ID, save stack pointer register value so that it can be restored, stack memory, size of stack memory, CPU time used so far by a process, list of waiting processes on a process, list of open file descriptors, state of a process which can be ready, running or blocked. Each process has its own standard input and output. The next two fields are used for retrieving next process in a round robin fashion. For term project, I am implementing pipe system call for communication between two processes. It creates a pair of file descriptors pointed to by FDS0 for reading and FDS1 for writing. The pipe is unidirectional in the sense that the two processes communicating over a pipe, only one of them can write and other will read from that pipe. Each pipe uses its own buffer. The writing process will fill the buffer and reading process will fetch characters from buffer. This buffer is a FIFO and uses a circular buffer data structure for its implementation. To demonstrate pipe system call, I am spawning multiple processes, each separated by a vertical bar on command line. Process on left side of vertical bar is going to write on pipe buffer and then read by a process on right side of the bar. All these processes are running in parallel, so they are demonstrating multitasking as well. Now I am going to demonstrate working of the operating system. I'll open a shell and first thing I will do is set date and time. So these two commands show use of SVC calls and timers. The system date and time is set using SVC call and time is being updated using flex timer. Now I'm going to demonstrate device independent I/O. I'm going to create a in-memory file. Then I'm gonna write character A in that file. I'm gonna close that file. Sorry, my bad. I'm gonna read from the file I've created earlier and I get this character A. So I'm gonna close this file. this memory map command list all list memories that have been allocated or which are free, and it sort of lists the memory location, the process ID which has allocated the memory, and size, and it also shows whether it's free or allocated. Now I'm going to demonstrate the application I have used for to demonstrate my term project. So what I'm going to do is so I will run echo command, and sends. So echo command prints prints the arguments to standard output. So I'm going to send output of echo command to input to sort command. So sort command expects a list of numbers which it sorts and then prints the sorted output to standard output. So I'm going to output it to the next command, which is unique, which accepts a list of numbers, list of sorted numbers, and prints unique numbers in that list, and then I'm going to print that list. So as we see, we have list of unique numbers we pass to echo command in ascending order. So that's about it.